Good evening, everyone. Okay, so welcome to today's extra session. So we completed our 12-week live sessions yesterday night. Today, an extra session was scheduled in order to, summarize all that we learned about this course, which is the elements of mechanical vibration. So when we talk about mechanical vibrations, the first question that arises is why do we even need to study about mechanical vibrations, right? What is even the need of studying this course? So, when we talk about a system, right, there are two possible ways that we can use a system. First is we design the system practically and just give it the input and see what output we are getting. But that way, it is costlier, it is very risky, and we don't know how the system is going to behave, right? Like for a motor, now we know since we have seen the motor, we have seen how it works, and we have an intuitive understanding of how a motor works, right? We are going to give the electrical input corresponding to which it is going to give us a mechanical output. And then we have this idea that if we increase the input power, we are going to get more output power, right? Now, but for the motor, we have the intuitive understanding, right? But is it always true for every kind of a system? Like even for a motor, if I apply some eccentric loading on it, what is going to happen? It is going to produce vibrations that I was not knowing because I don't know how the system is going to behave. So that is why it is essential that before going into the practical application of any kind of a system or any kind of a element, any kind of assembly of elements, it is important that we understand that what is the underlying physics behind it, right? And definitely mathematics is the best way of deriving how everything works. So what do we do? For a practical system, we try to create a mathematical model. Using that mathematical model, we now know or we can understand that how different kind of inputs is going to affect our output and what are the probable outputs that we can get, what are the inputs that we should avoid in order to avoid any kind of a catastrophic failure, right? Or any kind of a very high amplitude of vibration. Like for any practical system, like I was saying, for the eccentric weight on a motor or a rotor. So that is going to produce vibration. Now it will happen that during the resonance condition, right, at the resonance frequency, if our rotor is rotating, then what is going to happen? It is going to create very high amplitude vibrations which can lead to catastrophic failure of our system, or it can lead to at least failure of the system, right? And it is risky as well, because when we are working with very heavy parts which are made up of metal, we usually avoid any these kind of instability into the system, because it may happen that there is some breaking of some part and then flying off. It can go and hit some other machine, it can go and hit some person and cause many damage, right? So that is why mathematical modeling is the first step that we take towards applying a or using a system in the practical condition, right? So basically, we have a physical system. Okay, we have a physical system. What do we do? We create a vibration model for it. We create a vibration model for it. Okay, we create a vibration model for it, right? Now, when we create a vibration model, what do we get? We get we get the option now to understand how the system is going to work, right? How? Because from the vibration model, we are essentially getting a governing equation. We are going to get a governing equation. We are going to solve this governing equation, and from that, we can interpret what are the ways in which a system can vibrate, right? Now, there are two things that is to be kept in mind. That during this course, we studied the mechanical vibration for a linear system. Not actually for a linear system, but for the linear assumption of a system. Because everything is in this world actually follows a nonlinear behavior. But when the range of motion or actuation is very small as compared to its physical dimension, then we say that it works in a linear range. Or you can say that the linearity property actually it applies to the system for that point of time. And that is what we have learned for this course, right? We have worked on the linear behavior of the system. Linear. We're not going into the non-linear part because then it becomes a more difficult case and it is still evolving. The non-linear vibrations are still evolving and there are a lot of things that needs to be taken care of. Okay, so we are working on the linear system. Now, what do we essentially, what have we essentially looked on in this course? So, for a physical system, we saw the vibration models, right? We saw the probable vibration models that can be used for any kind of a physical system, right? Like yesterday, we again, we used the example of a cantilever beam that had a mass over here, which we solved during the week 1 or 2 live session, right? Where we had the same case. The only difference was that for the week 1 and week two, we considered this as a single degree of freedom system. We modeled it as a spring attached to a mass, and then we solved it for getting the natural frequency of the system. Once we get the natural frequency of the system, we can just use whatever the solutions that we learned for this kind of a system in order to get the behavior. But yesterday, what did we do? We used the concept of continuous system. We used the PDE, which are the partial differential equation, in order to get the equation for the natural frequency of this system, right? Now, maybe we should first talk about how do we get the PDEs or what are continuous system and uh, discrete system, like we have discussed earlier. So just to give an overview, first is maybe I should write it over here, need of vibration model. I hope that it is understandable that there are various needs like a robust design for quieter application, safety purposes, because then we can avoid the resonance condition, right? And once we avoid the resonance condition, we can ensure that the operation of the machine is under the safe condition. Okay, safety. And the last one is going to be for the monitoring. Now, what is monitoring? See, basically, for a system that is operating under a dynamic condition, there is some kind of vibration it is going to produce, right? Now, when the system is perfectly fine, there is no any kind of deformation, there is no any kind of like any kind of change from its original condition, right? And we say that the system is healthy. Okay, that is the term which is used for the health monitoring of a physical system, mechanical system. If it is said that the system is healthy, it means it is in the whatever it was designed when it was designed in a particular way. It is like that only. We say it is healthy, and then it there is a possibility that due to the high vibrations or due to some climatic conditions or due to erosion, due to corrosion, it may happen that some fault occur in the system. Now, because of those fault, there is going to be the change in vibration of the system. Like a healthy system, when operating under a particular situation, it is going to give us some kind of a vibration. We can monitor it. We can just see. We made a system. We saw how it is operating. Okay. We take the vibration data and we see that, okay, this is the data that we get for a healthy system under these conditions. Now, after 10 years, 20 years, I want to check that how the system is still behaving, or is there any kind of fault that is inside the system. So what do? After that, we again set the system under the situations that we considered earlier for taking the data of a healthy system. We then take another data under those situations only, okay, under those conditions, and then we compare that, okay, this was the data that we got for a healthy system, and this is the data after 10 years. So what is the difference in the data? Based upon that, we can judge that how much my system has degraded and whether still this system is in the condition that it should continue to operate, or should it be removed from operation and another healthy system should be put over there. Apart from that, now this is a very long-term situation. Like we left the system for 10 years to operate. We are not even constantly monitoring it. But that is not the case for system where a catastrophic failure can happen. Like for example, in case of turbines, right? In case of compressors, what happens is that even a very small amount of fault is going to cause a catastrophic failure of the system. So continuous monitoring of the system is very important. Continuous monitoring means we keep on checking the vibration data. Now you can develop a model that continuously check, or the person can sit and check. But anyways, the model is the best option. So basically, we feed in the healthy data and then we give it the knowledge of, like by ML algorithms, we can give the knowledge that, okay, if there is some this kind of a fault, let us say A fault, A we can say is, let us say for a gear, if we talk about a gear, if this is a gear, this is a gear, okay. Now what happens is that due to operations, due to continuous meshing of one gear with the other gear, there is some kind of a chip that is created on the gear. Chip means chipped tooth means this. It got blunt from here. Now what is this going to create in the final result? This is now going to give us different vibration data. So we are going to intentionally create this fault, let us say fault A, and then we are going to get the data, feed it into the algorithm. We'll create another fault B, get the data, feed it into the algorithm. Again, another fault C, feed it into the data. Likewise, we take the data for the probable faults that at least we know can happen, which can cause catastrophic failure at least. Because some kind of a faults, they are not going to show that much effect, but some kind of fault can show a very large effect on the system. So basically, we will first be concentrating upon how these the large output faults to consider into giving into the algorithm. So we'll intentionally give the fault to the system. Corresponding to that, we are going to take the data and we'll feed it into the ML algorithm that, okay, these are the faults, and upon that these are going to be the vibration datas. Okay, and we have already given the healthy vibration data. Now there will be a comparison of how the system is going to behave. After this, we apply that algorithm into the continuous monitoring of our system. So as soon as the system or the algorithm detects that, okay, there is a change of vibration data and it matches with some of the fault A, B, C or D condition, that time only the operation of the machine is going to stop to avoid any kind of catastrophic failure. Because for very large turbines and everything, if there is a catastrophic failure, it means that it can create a huge loss to the infrastructure, to the machine, and to the manpower. Okay, it can just erupt the whole building. So it is very important that that should be avoided at any cost. So continuous monitoring in those kind of a system is very important. And as soon as the system detects that, okay, this is the problem in the vibration data, so the operation is going to stop. So that should be avoided in any case. So that is why the vibration model is very important. It is very important in order to know how the system is going to behave. See, when we talk about strength of materials and fluid mechanics, we actually work on upon the stress strain relations. We work upon how the stress, bending moment, and these things are going to cause stress in the system, and what are the modes of deformation that can happen. So whatever it is, it does not talk about the dynamic behavior of the system. Correct? We don't know how the system is going to behave in the dynamic condition. Although when you will learn about nonlinear vibration, you will get to know that the same concepts of SOM are being used over here also. The only difference is that there we were not concentrating on the dynamic model, but in mechanical and nonlinear vibration, we are considering the dynamic model itself, because it is important that we know that how with time the system is behaving in order to know that what are the needs that I get from the system, what should be the input that should be given, and the input given in such form that even for the transient vibration also, there is no any kind of failure into the system, or it does not cross the bounds upon which it should never cross. Okay, so these are the needs of the vibration model. Now, talking about the first thing about when we talk about modeling of a system, we talked about it a lot, which was the degrees of freedom, right? So we define the degrees of freedom in many ways, whichever seems easier for anyone to understand, it can be used. Anyways, degrees of freedom is essentially the number of possible motions that a system can have, right? The number of possible motions that a system can have. Now, a system's degree of freedom depends upon how many mass points it is having, right? So the number, as many as we have the number of mass points, that many number of degrees of freedom we can have. So one definition of the degree of freedom says that number of possible motion of a mass into number of masses. This is the first definition that we learned, right? Now there was this second definition also, which was about that we consider all the possible degrees of freedom of a mass, and then we subtract the constraint. See, this is true. This is true for the case when we have identical kind of a masses, or masses that have identical possible motions. Now, if I have a mass that has the freedom to oscillate in a particular direction or move in a particular direction, and then we have a second mass that has the freedom to translate and oscillate as well, okay, to rotate about a certain axis, then in that case we just cannot apply this, because the two masses will be should have been considered in a different way, because one is having 1 degree of freedom, the second one is having 2 degrees of freedom. Okay, so this is true, but for a symmetric case where every kind of a mass is going to have the same possible motion that is being allowed to it, right? So that is for that case. There is another kind of a definition that we studied, which said that number of possible motions minus number of independent constraint. Now, what does this mean? This means that, okay, for a mass, I have a number of possible motion. Like in a 3D space, three-dimensional space, I have a ball, which has a position vector P. How many degrees of freedom does it have? 3. It is going to have 3 degrees of freedom. Now, if I constraint its movement, I constrain that, okay, this ball is always supposed to be in contact with the XY plane. It is always supposed to be in contact with the ground. So what have I done? I have constrained it, right? So it is going to have how many degrees of freedom in that case? 3. Now, mind it, here I am talking only about translation. I am not talking about rotation. Or maybe if we do talk about rotation, then in that case, this is going to have 6 degrees of freedom in that case. Okay. And now when I constrain it on a plane, that it should always lie on the XY plane, how many degrees of freedom it is going to have? Firstly, it was having 6 because it was free to translate in the 3 direction and rotate about these 3 axes, right? Now I've constrained it that it should always be on the X and Y axis, which means it cannot go into the Z axis. So first is it lost one minus, it lost one constraint, or it got one constraint and it lost one freedom to translate in the Z direction. So one is gone. Second is about rotation. It is still going to rotate about Z axis, right? Because for rotation about Z axis, it has to just travel in the XY plane. So that is possible. But then what about the rotation about X axis and Y axis? For that, it has to go in the Z axis, which I have not allowed. So then there is minus 2, two independent constraints which are related to the rotation about the X and Y axis specifically. So now how many degrees of freedom it is going to have? 3 degrees of freedom, right? 3 degrees of freedom. So one constraint that I constrain it such that it is always supposed to lie on the XY plane. So the ball should always be on the XY plane. Reduces its degrees of freedom from 6 to 3. Likewise is the case when we consider another kind of system also. Like for example, if I have two masses, mass m1, mass m2. Okay. These m1 and m2 are going to have independent motions x2 and x1. Right. Because they are independent. M1 can have a motion x1 and m2 is going to have another motion x2, which will depend upon that mass and the spring stiffness and the relative contraction or relaxation between them, both of them, relative distance between them, right? And they are independent of each other. They are not dependent on each other because there is no constraint that is binding it. So the degrees of freedom is how much? 2. There are 2 point masses. And these every point mass has how many degrees of freedom? 1 degrees of freedom. Why? Because it is made to oscillate only in this direction. Though it is in the two-dimensional space, but about this axis, it is not allowed to oscillate. In the z-axis, it is not allowed to oscillate. So it can oscillate only in the x direction. So if it is oscillating only in the x direction, what is going to happen? It is going to have only 1 degrees of freedom, no? Only 1 degree of freedom. Now there are 2 point masses, so there is going to be 2 into 1. So a total of 2 degrees of freedom it is going to have, right? Now corresponding to those 2 degrees of freedom, what is going to happen? We are going to find 2 degrees of freedom equation, two equations we have to solve simultaneously in order to get how the system is behaving. But what if I now try to bind it or apply a constraint on it such that like this. Now this is a rod. Now this is a rod. I've attached M1 and M2 through a rod. So then what happens? Well, this rod does not let any relative motion to happen between M1 and M2, which means now M1 and M2 collectively behave like a rigid body. So wherever M1 goes, M2 goes, and the only thing is that the difference between them, between these two, is always going to remain constant. They are going to have the same velocity, they are going to have the same acceleration, because now they are behaving like a rigid body. This is the concept of rigid body. Rigid body means every point in the inside that rigid body is going to have same vibration, is going to have same acceleration, is going to have same velocity, and the relative distance between them is always going to be the same, right? So if I am able to take out the position of one point, I can take out the position of other points just by calculating how much is the distance between them, because it is always going to remain the same. So now I have constrained the system by applying a rod. Now how many independent constraints are there? One. So the new degree of freedom is going to be 2 minus 1, which is 1. So now the system is having only 1 degree of freedom. I hope it is clear. So this was the second definition of degrees of freedom. Now there's a third definition also. There's a third definition also. I won't say third definition, but these are the possible meanings of degrees of freedom. See, degrees of freedom is not a very absolute thing that, okay, if I have this number of masses and this number of possible motions, then this into this is always going to be the degree of freedom. That is not true. Because now if I take again, like I've discussed earlier also, I'm just taking this example in order for you to remember this. This is a mass, and like this. This is a pendulum. This is a pendulum. How can it oscillate back and forth? It can oscillate in the back and forth. Something like this, right? So if we look at like this, we know that okay, it is oscillating in the xy plane, right? So is it having 2 degrees of freedom? Well, that is not true for this case, because you remember that for a pendulum we consider its degree of freedom as 1. Then how are we getting 1 degree of freedom? Because if you look at this clearly, what did I say about the degrees of freedom? A mass is having a 6 degree of freedom if it is in the x, y, and z plane. So earlier this pendulum was having a 60 degree of freedom, or the mass was having a 6 degree of freedom. Then it was attached by a mass, by a string or a rod to some reference point, right? Now what does this attachment do? What does this attachment do? Firstly, it constrains my system to be in the XZ plane. To be in the XZ plane. I'm not saying that to translate in the XZ plane. To be in the XZ plane. So if it is in the XZ plane, what does it mean? Firstly, it has already lost 3 degrees of freedom, right? Because it already lost the translation in the Y direction, right? And then it lost the rotation about the x-axis and the z-axis, because it can now only rotate about the y-axis. So it has already lost 3 constraints, as we learned in this example, right? But what is another difference? See, another difference is that for that case where we considered that when the ball was constrained to be in the xz plane, we considered that the translation in the x and y direction was also allowed, right? But here, when we constrained it through a rod in the reference, what happens is that now this mass can only rotate. Now, this mass can only rotate about the y-axis. No translation is possible in the x-axis or the z-axis motion. So, essentially, it has again lost 2 degrees of freedom. 2 constraints are already imposed. So, a total of only 1 degree of freedom is allowed for this pendulum, and hence it's a 1 degree of freedom system. So that is one way of understanding it. Another way of understanding is that the number of coordinates, minimum number of coordinates that are required to, give the motion of the system, which is also known as a generalized coordinate. Generalized coordinate are the coordinates, they are the minimum number of coordinates that are required in order to find the motion of the system. So here, though my system is oscillating in the x and z plane, but I need only one coordinate, a generalized coordinate, in order to find out the equation of motion. Now, from that prospect, also I can understand the degrees of freedom. Like for example, I'm not able to understand that what is the number of possible motion minus the number of independent constraints. So then what I will do, I will then think that okay, mass, it is rotating, so it is in the xz plane, so it can have x at any position, it can have a position x and a position y, right? But then x and y, it is going to have two positions. Now it suggests that okay, it is having 2 degrees of freedom, but then I'll think about that what are the other things. The other things is that this x square plus y square is always going to be equal to L square. So I can always write y in terms of x. So I need only one coordinate in order to write the other coordinate, right? Because only one independent coordinate. The other is dependent on the first coordinate, like from this relation. So I need only one coordinate. So this is essentially a 1 degree of freedom system. So the degrees of freedom, you can also write it as number of generalized coordinate to fully find the motion of the system. This also we can understand like that if I'm not able to understand that. So these are the three possible ways in which we can understand the number of degrees of freedom. Now, degrees of freedom is very important, and it is the most important plus the first step towards modeling of any system, right? Because then only we can understand that what kind of equation we need to find out for the system. If my system is a 1 degree of freedom system, I'll need only one equation, right? If it's a 2 degree of freedom system, I'll need to find out two equations, two independent equations in order to find out the overall motion of the system. So it is first very important to find out the degrees of freedom, as we learned, and we have already worked upon many questions by finding out the degrees of freedom and then doing it, doing so like solving the equation and everything to get the response. And I'm not going into that again because we've already done it a lot of times. So this was about the degrees of freedom. Now, once we have already understood about the degrees of freedom, if I talk about the practical application, see, now we have done so many questions which are related to single degree of freedom, 2 degree of freedom, multi-degree of freedom systems. We have also talked about the continuous system. Now is the concept that how do we use it practically? So practically up till now it is clear. We look into the system, we find out its degrees of freedom. Okay. Till now we know how to do it. Okay, we have done it for many systems. First thing is, how do we find out the degrees of freedom if it's a continuous system? Depends upon what application I'm into. If the linearized and 1 degree of freedom system assumption is going to work to get the response of the system, we can do that also. If it is not good for us, we can go up to the continuous system. We can model it as a continuous system as well. But this depends upon what kind of a accuracy and what kind of a computation cost we are able to bear for that particular kind of a system, and how much accuracy do we want, because when we are going from a single degree of freedom to the continuous system, the difficulty level also increases, the computation cost also increases. For a 1 degree of freedom system, I know the exact solution, right? For a continuous system, it is difficult because it's a partial differential equation and it's applicable to only certain kind of system. But what if I have a very complex system that has a combination of beams and bars and everything? Then it becomes difficult. Then we'll have to go into FEM, finite element modeling, and then we'll have to solve it through numerical techniques to get the solution. Anyways, the thing is that the closed form solution is always most reliable, but then in case of practical application, closed form solution is always not possible because it comes with a linearized and the less degree of freedom system assumption. So it depends upon how do we want our system to behave, and depending upon that, we can choose that what kind of a model is best for our system. So then, if I choose my system to be a 1 degree of freedom system, right? If I choose my system to be a 1 degree of freedom system, so it is easy for me, right? Because for 1 degree of freedom system, we have done a lot of exercise. We have understood everything as of now. So what was a 1 degree of freedom system? Nothing much, just a spring and a mass. That's it. And based upon this, we tried finding out the omega n, which was the natural frequency. Omega n, which was the natural frequency. Why was natural frequency important? Why was natural frequency important? Because for this mass, if I give it a perturbation, if I give a perturbation x naught to this mass, what is going to happen? It is going to oscillate with what frequency? With the natural frequency. It is going to oscillate with the natural frequency. So for any system, we try to find out the natural frequency, because if any kind of a perturbation is given to the system, it is going to oscillate by virtue, it is going to oscillate by the natural frequency. Now, it is important that we understand the natural frequency also, because, okay, if the damping is very small in the system and it is almost negligible, then understanding the natural frequency is very important, because then the system is going to oscillate with that, right? Now comes the case of forcing. Whatever some kind of a forcing is applied on it. F sine of omega t. We all know that the system is going to see, or system is going to have resonance condition when this forcing frequency is equal to what? The natural frequency. So we have resonance if omega is equal to omega n. Now what does this cause? This is going to cause high amplitude vibrations. Resonance is going to cause high amplitude vibrations, which is which is to be avoided in the practical case, because high amplitude vibration, see, whenever we are modeling a system, we don't consider, or we don't model it for a high amplitude vibration, because we have a space constraint as well. We cannot model a system in such a way that okay, it can oscillate as much as it want. No, it is always having a constraint about the amplitude of vibration, and anyways high amplitude vibration is not good for a system. It can cause failure of the system as well. Okay, it is going to create a lot of noise, and it is not at all acceptable, not even recommended. So it causes high amplitude vibration. Now we have to avoid it, which is fine. So we find out the resonance natural frequency just for this case in order to avoid the resonance condition. Second is, okay, I understand that the damping is small, but damping is present. In every system, the energy damps out, be it because of the structural damping, be it because of the viscous damping, be it because of the friction, be it because of the air resistance. Anyways, the energy is going to get dissipated for any kind of a vibrating system. Okay. So if the energy is getting dissipated, then how do we work? Now, for this, our equation was very simple. Mx double dot plus kx is equals to 0. Okay, first getting into damping, first let me just give you a revision about how did we find out the natural frequency. Omega n, it was simply under root of k by m. It was simply under root of k by m. Natural frequency was under root of k by m. Okay, so if it was under root of k by m, then where is the difficulty? Because it's a simple system. What if I have a complex system? Then there were other ways that we discussed about finding the natural frequency. One was the energy method. Total energy was constant So we used d of total energy with time equal to 0. This gave us the equation of motion. From the equation of motion, we found out the natural frequency. Correct. Another way was by the virtual work. We use the principle of virtual work in order to find out the equation of motion. And then from that equation, we can find out the natural frequency. Third one is that omega n is equal to under root of k effective by m effective. Okay, which means we find out the effective stiffness and we find out the effective mass. Like if you remember that for this system only, the natural frequency was under root of k by m when the spring was considered that it does not have any mass. While if now we consider that spring has a mass, okay, let us say m naught, then in that case we found out that we have to just replace m with m plus m naught by 3. And we said that okay, that is the effective mass. Likewise, we can consider the effective stiffness as well. How? Like for example, we have two springs in parallel, then one in series, and then the mass is attached like this. So either we'll have to just solve the equation of motion, or we can just use the concept of finding the effective stiffness for the spring in parallel and spring in series, and we get the k effective and write the omega n as under root of k effective by m, right? Which can be used. Okay. So this was how we found out the natural frequency. Anyways, we did a lot of questions regarding the finding out of the natural frequency, and we practiced a lot. So I think it is clear to all of us. Anyways, now this was the case when we considered a undamped system. What about a damped system? When the damping is present inside the system. Like for example, if I consider the viscous damping, there is a spring, this is the dashpot, and there is a mass. How do we deal with these kind of system? And why is even required to find out the natural frequency? Why is it even required? So see, when we are talking about a damped system, first thing, if you are going to give it any kind of oscillation, it is going to damp out. Okay, if there is no forcing present in the system, the damping is going to what? It is going to take up whatever energy is given to the imparted to the system in terms of the perturbation energy and make it equal to zero after some time. Right? So what is going to happen is that if I give it some initial perturbation, it is going to damp out either like this or either like this or like this. These are the possible ways of damping. Damping of initial perturbation. Okay, this is for a unforced system. I hope it is clear. This is for a unforced system. Okay. Now the question is that okay, this is fine. It is going to damp out. But then if it is going to damp out, then why do we even require the concept of resonance or natural frequency for a damped system? Right? For a damped system, why do we even require? So essentially, for a damped system, this is the case for the non-forced condition. What if some kind of a forcing is applied to the mass? Some kind of forcing is applied to the mass. So if some kind of forcing is applied to the mass, only the energy which is because of the perturbation is going to damp out, and the transient vibration is going to damp out. Apart from that, there is a constant flow of energy in the system and constant dissipation of energy. It is going to come to a case where this is equal, and the system is going to have a steady state vibration, despite of the fact that the energy is being transferred to the system and the energy is getting dissipated at the same time. The system is going to show some kind of a vibration, which we call it as a steady state vibration. Correct? So if I apply forcing, our response consists of two things. One is the transient vibration plus the steady state vibration. The response is going to have both of them, some transient vibration and some steady state vibration. Now, because of the presence of damping, this transient vibration is going to damp out. Okay, the transient vibration is going to what? It is going to damp out. The transient vibration is going to damp out with time. So we'll have only steady state vibration. Okay. So we are only concerned about the steady state vibration. So then where is the role of omega n? Because for the steady state vibration, the response will depend only on omega. The response will depend on, okay, I should take another slide. Yeah. For a steady state vibration, what is going to happen? It will depend on, it is going to depend on the forcing frequency, omega. Other than that, it does not care about any other thing. Okay. So if the steady state vibration is going to depend on the forcing frequency omega, then why do we even require the resonance condition? Well, again, because it will depend on omega. Omega can have any value. And again, if omega is equal to what? Omega n. Then despite the presence of damping in the system, it is going to have resonance, which is the high amplitude vibration. Although it is important to note that the peak, like for example, if this is omega n and this is the omega axis and this is the amplitude axis x bar, this is the resonance condition. This is going to improve like this. Not improve it, the amplitude is going to reduce like this. So this is for, I should not write eta as of now. I should write C is equal to 0. So C is equal to C1 and this is for C2. So these are the cases for C1, C2. Anyways, for here, C2 is greater than C1. Okay. So this is how the amplitude is going to reduce. This we have learned about earlier also. So anyways, just for the reference, I'm writing mx double dot plus cx dot plus kx is equals to 0. So this is the C we are talking about over here. So this is how it is going to affect. So it is important to note over there that even for a damped system, we need to understand the resonance condition, or we need to know what is the natural frequency of the system, because at that frequency we are going to have high amplitude vibration. Although the amplitude of vibration is going to reduce with the increase of the damping value, but still it is important to note so that we avoid that particular frequency, or we don't go near to that particular frequency in order to avoid any kind of a failure. So I hope that now it is understandable that although my system is damped, I still need to find out the natural frequency, which I can get after considering or after removing the damping from the system. Not practically, but in the mathematical model. Okay, because it will be easier, right? With the damping, it becomes difficult. Without damping, it becomes easier in order to find out the equation of motion and then find the natural frequency of the system. And then you can add the damping into the system and do the particular analysis. Okay, I hope it is clear. Now, this was the case for the damping. Now, damping can be added in the system in many ways, right? We basically define Cc, which is the critical damping, as under root of m by k. If you people have must gone through the book, you must have known that for the critically damped system, the time of convergence is the lowest. Okay, so if we are having a transient vibration, then for the critically damped system, it is going to reach the steady state in the least time. Okay, apart from that, we have C greater than Cc and then C less than Cc, which we call as undamped, not undamped, sorry, it is underdamped system, and this which is the over damped system. So for the underdamped case, we are going to have some vibration kind of a thing. For the overdamped case, the behavior is going to be straight, like this. No transient vibration. Okay, so these are the case of overdamped and underdamped system. And these are the three possible cases that we are going to have. Anyways, we can have a critically damped system as well. So these are the three possible cases that we can have. Now it will depend upon how our practical system is, that we can have a critically over or underdamped case. Okay. Either it is going to be a property of my system by default, or what I can do is I can make my system, like for example, if I'm talking about an elastomer, rubber, or that kind of a material, what I can do is I can tamper its properties by introducing some particles, or how it is being manufactured. I can tamper it in order to get a particular kind of a behavior, which can be critically damped, underdamped, or overdamped. Okay, so it will depend all upon our practical application. See, it is very important to understand that all this course we have been learning about what is a critically damped system, what is an underdamped system, and everything. But in practical situation, there are only two things that is in our hand. First, we have the system, we find out the properties, and then know what is this, how is the system going to behave. Second way is for the system we have to manufacture. We will we are going to manufacture the system in such a way that these parameter values comes under how we want our system to be, and then get the particular solution from the system. Okay, I hope that is clear. So yeah, these are the cases for underdamped, overdamped, and critically damped case. Okay, now coming on to what are the types of damping that can be there in the system, right? We did a lot of work on it, that what kind of a damping could be present in the system. Anyways, let me just write one more thing. We This was the equation. Do you remember? This was the equation that we wrote from here in the normalized form, right? Eta was what? It was the damping coefficient. Sorry, damping ratio. Damping coefficient was C only. This was the damping ratio for us, and omega n was the natural frequency of the system. Omega n was the natural frequency of the system. So we usually write it in this form because it is easier for us to interpret then. Okay, now just a second. Okay, so this was the case. Now, what are the possible dampings that we studied about? One was the viscous damping, which was C x dot, right? Viscous damping, which was C x dot. We considered the force in the form of C x dot, and C was the damping value. C was the damping value. And if you remember that for this case, we had this underdamped system. We introduced the concept of what? Logarithmic decrement. We introduced the concept of logarithmic decrement, right? So why was there a need of logarithmic decrement? Because if I have a practical system and if I want to analyze that how my system is behaving, I need to find out the parameter values, right? Like for this, I need to find out the parameter values. So what are the parameters over here? There are only two values. One is eta and the other one is omega n. Okay. So I need to find out one eta and one omega n. So omega n is easy for us to find. How? Because we are going to give some initial perturbation to the system and then we can find out what is going to be the omega n, right? We can find out the omega n. Or basically for an underdamped system, we actually have a damped natural frequency, right? We have a damped natural frequency that also we can find, but for a practical system, omega n, finding omega n is not that difficult because we know the mass of the system and we can find out the stiffness by applying some constant load on it. Or what we can do is we can find the value of eta, and from this graph only we are going to get the value of omega d, damped natural frequency, right? Which is going to be what? This thing. From here we can get omega d. Okay, and from the logarithmic decrement, we were getting eta. Using this, we can get the natural frequency because omega d was nothing but omega n into under root of 1 minus eta square. This was the equation for the damped natural frequency. Now, so the first thing is we need to find eta. How do we find eta? Using the logarithmic decrement. The logarithmic decrement said that this thing is what? It can be written like for any xi and xi plus 1, we can write xi is this and xi plus 1 is this. Okay, so we can write ln of xi by xi. Okay, this is xi and this is xi plus 1. Okay, so we can write xi by xi plus 1 as what? 2 pi eta divided by under root of 1 minus eta square. So for the practical condition, if I give some initial perturbation and I record the xi value and xi plus 1 value, I can put it in this equation and solve for eta to get the value of eta. Once I get the value of eta, I get the value of omega d, I can get the value of omega n, and now I can use this equation to get the behavior of the system. Now it will depend upon the value of eta, right? Because eta is, it can be small, it can be large. If my eta is very small, eta is very, very smaller than 1, then ln of xi by xi plus 1 is going to be what? 2 pi eta. Because this is for a case when when eta is very small. Okay. Anyways, you can go into the assumption, but I would suggest that now we have enhanced techniques, we have MATLAB, we have scientific calculator. So this is a better option. We can just solve it using MATLAB or anything. It is easy, very easy. So this was the case. Now the question is, for this, I need to find out the amplitude value for the two consecutive peaks, right? But what if I'm not able to? I don't have a, let us say, measuring device that is able to measure it. Frequency, I cannot tune the frequency up till that amount. I don't know how many oscillations it is taking or something like that. I'm able to measure the consecutive peaks only after n intervals, for example. Then what is going to happen? What are the possible options that we can take? So for that case, if I'm not able to take two consecutive intervals, so I'll have to take n consecutive intervals. For that, we can define, like for example, I have the value of xi or x1, and then I have a value of xn plus 1. So there are n intervals that has happened between them. So how can we write it? See, we know that this ratio is always going to be constant. The ratio is always going to be constant. So if I want to write this, what I can do is I can write it as x1 by x2 into x2 by x3. I'm not using crossover here, I'm using dot because then it will have a confusion. I have x3 by x4 into dot 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 xn by xn plus 1. Okay. So then what it is going to give me? It is going to give me that these things are always going to be what? Delta, delta, delta. The ratio is always going to be the same. That is what logarithmic decrement is all about. The ratio is always going to be the same. Okay. So what will we have? We will have this as e to the power delta to the power n. E to the power n delta is equal to xi x1 by xn plus 1. Okay. So we are going to have what? We are going to have delta, which is the logarithmic decrement, as what? As what? Delta is 1 by n ln of x1 by xn plus 1. Okay. And then we have to equate it to what? Again, the same thing. 2 pi eta by under root of 1 minus eta square, and hence x1 by xn plus 1 can be used like that. Okay. So this is how we are using the logarithmic decrement. Now it was useful for the practical application, definitely. Over here in this course, what did we do? We were just mathematically modeling and then finding out the solution, right? But that is the, last step, I would say. The first step is, how do we interpret our physical system? These mathematical modelings and these things, they are not the basic thing. They come always secondary to what is our practical system. They are always used in order to understand the practical system, in order to mathematically or theoretically interpret the system, right? So first is the understanding of the practical system, how the practical system is behaving, how to model it. Once we get the model, then we have to find out the parameter values. And using these techniques, like the concept of logarithmic decrement, we can find out what? We can find out the values of eta, omega d, and then omega n, put it into the equation, and then simulate it for different kind of inputs, different kind of a condition, different kind of a forcing, in order to understand how the system is going to behave. Okay. Now this was the for the viscous damping. Then we had another kind of a damping, right? Which was what? Coulomb damping. Coulomb damping, which was based on what? Which was based on friction, right? Which was based on friction, wherein we were using the concept of friction. So if we have a system like this, with mass like this, and we have a mu n, friction, right? So it is going to dissipate the energy. But how is it going to be? See, this in this case, the damping is can have only two values. One is plus mu n, another is minus mu n, right? It will depend upon the values of x. So for that case, how did we see? We saw that for this case, the behavior was something like this. It was a straight line. Remember, it was a straight line. It was a straight line, right? And if this was x, let us say, this was x, this was what? Minus x plus 2 delta. And delta was what? Do you remember? Delta was delta was what? Delta was having a value of mu n by k. K was the stiffness of the spring. Mu was what? Mu was the coefficient of friction. And n was the normal force. So basically, this was nothing but the friction force, mu into n. Okay, so this is how we got for that Coulomb damping. Likewise, we had structural damping as well, and all those kind of a thing. Hysteresis damping, everything we learned. I'll just write structural or hysteretic damping we had. Okay, so these were the possible damping models that we considered. Now, after this, we did all the analysis. We solved many numerical problems. We learned about how many how many oscillations has passed by, number of oscillations that has passed by before the amplitude reduces to a certain amount, and this was all for the basis of finding the parameter values for comparing it from a practical condition. Anyways, this was for a translatory system. Likewise, we can have a rotational system as well, right? If this we have a rotatory system and this is rotating something like this, we can have this as well. It is going to go with the same track. Okay, the only difference is going to that over there we were having x and k. Here we are going to have theta and rotational stiffness. Okay, everything is going to be the same. The concept is going to be the same. Now comes, we learned about what? We learned about free vibration. We learned about forced vibration when we were having something like sine or cos, harmonic forcing. Now there can be transient forcing as well, transient vibrations. Because of transient forcing, it is not always true that we are always going to give a sinusoidal kind of a vibration, right? It may happen that the forcing could be random also. It could be impulse also, and like that kind of a thing. So we learned about that also. We learned about how to find the solution for a system when the forcing is of the type force with time is some random value like this. So basically, if you remember, we learned about the impulse forcing. We learned about how if we model it as an impulse, a small impulse is given to the system, how it is going to behave, and then what we can do is we can just break it down and form it in the small part of impulses, and then just add the solution, which we were doing because of the principle of superposition. I hope that you remember it. Principle of superposition, very important. Principle of superposition, very important thing because it is applicable in this mechanical vibration concept, but it is never applicable in non-linear systems. It is very important, very important. Principle of superposition says that if I am applying two forces into the system, like if I apply a force F1 and I get a solution X1, then apply a force F2, and then I get a solution of x2. So if I apply a force F1 plus F2, I'll get a solution of x1 plus x2. That is what we did over here, na? What did we do over here? We divided f with respect to time in terms of what? In terms of f1, which was at 0, plus f2, which was at t, plus f3, which was at 2t, plus f4, which was at 3t, and likewise plus dot 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 fn at n minus 1t, right? This is what we did. This is how we divided our force F. Now what were we doing? We found out the solution for F1, F2, F3, F4, Fn, and we add the solution. That is why, because we are considering that the principle of superposition is applicable for a system. But that is not always true for every physical system, especially if the system is operating beyond the linear range. It is not always possible. Okay? So it is very important to note that the principle of superposition is applicable only for the linear range of a system, not for the nonlinear range. So this is what the principle of superposition is. If I apply n kind of a forces to the system and I find out the solution for single forces for F1, F2, F3 and F4, and if I get the solution and just add it, that is going to give me the total solution of the system if the whole F is applied in a single go simultaneously. Okay, so we say that the principle of superposition is applicable, and it is applicable for linear case, not for nonlinear case. Okay, principle of superposition. I hope it is clear. So that is how we did for the impact loading or in general forcing other than the harmonic forcing. Okay, now I hope this is clear. This was for the single degree of freedom system, right? Apart from that, we also considered some applications like vibration absorber and vibration damper, where we were having two masses, or we were having, like, for example, we had a mass spring dashpot. This was connected to a reference, and this reference was oscillating by some y. This reference was oscillating with some y. So we defined the displacement transmissibility ratio. We defined the displacement transmissibility ratio, right? We defined it, that how the y amplitude or the y motion is affecting the x motion. Okay. Likewise, we define the transmissibility ratio for a 2 degree of freedom system as well. Like, for example, if I have a mass m1 which is suspended from a reference through a spring k1 and c1, and then that mass is given some kind of a perturbation. Then we have another mass m2. There is some forcing that is happening on m2. So how these two are going to, affect each other, and what is going to be the transmissibility ratio of m2 with to m1, right? So that we are going to get from the concept of transmissibility ratio. And it is very important to understand that, as we did it in the earlier problem also, about tuned mass dampers. What was a tuned mass damper? So if we had a mass m1 and then we had a spring and we have a mass m2, so we defined a tuned mass damper, which was something like, if I have M1 and M2, and if I give the forcing at a frequency, or if I make M2 and the spring K2 such that it is going to have a frequency, uh, so that M2 is going to have all the oscillation and M1 is not going to have any oscillation. It is going to have a zero amplitude. Transmissibility ratio is going to be zero, right? And that was also the case. So we learned it about in the vibration absorber and tuned mass damper, right? And there was undamped mass damper and damped mass damper, both cases. And we did a lot of questions about it as well, so that it was understandable that how do we work. So this was all about single degree of freedom system. Now comes the concept of two degree of freedom system. For the two degree of freedom system, like for example, even if we consider a cantilever beam, we have the freedom to choose it as to model it as a one degree of freedom system, two degree of freedom system, multi degree of freedom system, or as a continuous system itself. So definitely with the increase of degrees of freedom, the accuracy of the system increases. So for a two degree of freedom system, we have two independent coordinates to work upon. And we are going to have two differential equations that will be coupled to itself, and then we'll have to solve it to get the solution of the system. However, again, likewise, as we proceeded with the single degree of freedom system, we did it for the two degree of freedom system as well. If we were having a resonance condition in one degree of freedom system, we'll have a resonance condition in two degree of freedom system as well. The only difference is this time is that we are going to have two values of natural frequencies, right? Two values of natural frequencies, and corresponding to that, we are going to have two eigendirections or eigenvectors along which, if the motion is happening, then it vibrates with only a certain kind of a frequency. So, if you remember, if I made you understand this by the concept of geometry, that if we have a x-axis and we have a y-axis and we have a point P, then how do we write its position vector? We write it as px of I cap plus py of j cap. This is how we were writing the position vector, right? And using this, what did we do actually? We had I and j, which are two independent unit vectors, and we wrote a position vector using those two independent unit vectors as a linear combination of both. Correct? Similar concept comes when the degrees of freedom of a dynamical system increases. For a two degree of freedom system, if I get two independent solutions, then I can just write a general solution as a linear combination of those two independent solutions. Correct? Now, first thing is, how do we find out those two independent solutions? So we know that for a system, there's always going to be eigenvalues, two eigenvalues and two eigendirections or two eigenvectors, such that the movement in those two directions will be independent of each other. In the movement in those two directions will be decoupled with each other, right? So if I have, for a two degree of freedom system, let us say, like mass m1, m2, like this. Okay, let us for now assume that this is all the three are k. So this is a two degree of freedom system. M1 is going to have a motion x1, M2 is going to have a motion x2. This is a two degree of freedom system. X1 and x2 are going to be its motions, right? So if this is the case, how do we proceed with this kind of a system? Now, for M1, or we are just going to have two frequencies, okay? Omega 1 and omega 2. Corresponding to omega 1, what are we going to have? We are going to have a eigenvector x1, and corresponding to omega 2, we are going to have a eigenvector x2. Okay, these are the two possible ways. Now the thing is that corresponding to omega 1, we are going to have a certain kind of a motion. Okay, so if, for example, I give the motion in this direction, both are in the same direction. One kind of a mode is going to one kind of a mode is going to get up. Okay. Now it is important over here to note that in this case, the solution of x1 and x2 is going to depend upon what? It is going to depend upon the vector, eigenvector, which is related to omega 1, and it is going to depend only on omega 1, not on omega 2. There will be no component of omega 2 or x2. While for the other case, if I give perturbation of one in this direction and the other in the opposite direction, what is going to have? what are we going to have? We are going to have the solution in terms of omega 2 with the contribution of only the eigenvector x2. So these are two independent solutions. We are saying that these solutions are independent. Why? Because for one kind of a perturbation, only omega 1 is having a role. Omega 1 and x1 are having a role. And in the further classes, we learned that these eigenvectors are actually orthogonal to each other, right? The mode shapes are orthogonal to each other. So they are at a orthogonal direction with each other, x1 and x2. So if we give the first case of perturbation, only x1 and omega 1 are going to have a role. If we give the perturbation such that only omega 2 and x2 are going to have a role, so we get two independent solutions corresponding to these two, and we can find the general solution in terms of the linear combination of these two, right? Similar was the case. Now this is the case when we are talking about undamped case. What if the damping is present in the system? When now damping comes inside the system, this does not have any role. The mode shapes and everything not going to affect. The only thing that is going to matter over here is that to avoid resonance condition. We have two omega 1 and omega 2, right? We need to avoid this in the practical condition because at omega 1 and omega 2, we are going to have what? We are going to have maximum amplitude of vibration, which can cause catastrophic failure of the system and which is not recommended also. But why do we even need to have very high amplitude of oscillations, right? We have space constraint and everything. And if our work is happening at a low amplitude of oscillation, why do we even require it? So for a damped system, avoid the forcing at or near the resonance condition, which is omega 1 and omega 2. Okay, so this is the thing. Now, this was for a two degree of freedom system, right? But then we talked about multi degree of freedom systems as well. We talked about multi degree of freedom system as well. Multi degree of freedom system means we are going to have one mass, two mass, three mass, maybe n masses. So this is a multi degree of freedom system. Now, for a multi degree of freedom system, what do we do? See, if I am having n masses, definitely I'm going to have n degrees of freedom, n omega n and n eigen values. So we say firstly modal frequencies and mode shapes. Just the same thing which is related to what we studied about eigenvalues and eigenvectors. See, eigenvalues are not directly our frequencies, but in modal analysis, we take out the frequencies through those eigenvalues, and then we say that, okay, these are the modal frequencies and the mode shapes corresponding to that. So what do? We try to write the equation of motion using the matrix form. How? Like this, m x double dot c x dot k x is equal to f, right? Where m is going to be what? It is going to be n cross n matrix. X is going to be what? It is going to be a n cross 1 matrix. So M is going to be of the form M1, M2, M3, dot Mn. It will be a diagonal matrix. Okay. C and K are not going to be diagonal matrix. It will depend upon how the springs are connected and everything. Okay. And for example, K, if we want to write, it is going to be something like 2K 2k dot 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 like this. It is going to be k minus k. Likewise, it is going to be. Okay. Anyways, so this is the case that can happen. Apart from that, x, how is x going to be? x1, x2, x3. This is how we write it in the matrix form. Now, in order to find out the modal frequencies, what can we do? There are two ways, two possible ways, whichever feels good to you. I feel the way other way better. Like for example, I assume x as what? Some x naught sine of omega t. Then we put it in the main equation. So we get minus omega square m x plus k x is equals to 0. We are for now not considering forcing and damping because when we want to find out the natural frequencies or the modal frequencies, we don't have to consider the damping or forcing because it does not depend upon the damping and forcing. Minded, it is only for the linear system. When we talk about a nonlinear system, the resonant frequency is even going to change with initial condition. Forget about the parameters. You think even the initial condition is going to change the resonance frequency, the harmonic frequency. So parameters, so definitely it is going to affect. This is only for the case of linear system. So this we get, so we can write it something like k minus omega square m into x going to be 0. Now x cannot be equal to 0, right? Because if x is 0, there is no kind of vibration that is happening in the system. So x cannot be equal to 0. So the only possible solution is that this goes to 0. Now this is a matrix, right? So we what do? We find the determinant of this and we put it equal to 0. This is going to give us a characteristic equation, right? And mostly its power is going to be omega square, not omega to the power 2n. So we are going to get 2n in the equation and then we'll have to find out. And then we will have to find out the values of omega for which we are going to get the modal frequencies. I hope it is clear. Corresponding to modal frequency, then we can find the mode shapes. And mode shapes is important when we talk about undamped or especially unforced kind of a vibration which happens because of some initial perturbation. Because when we give the, maybe I should write it also, the input, if input is near to a particular mode shape, if the input is near to a particular mode shape, comma, it is going to excite that mode shape and the frequency of oscillation is going to be the corresponding modal frequency. Okay, I hope it is clear. It is going to be the corresponding modal frequency. Okay, I hope it is clear. So this is what happens in a particular case. Now, this is for a undamped system, because for the damped system, it is going to give us that motion, but it is going to damp out with time. So basically, when we talk about structural vibration, the damping is present over there, but the damping is very small, right? So this is very important. Mode shapes and its analysis is very important over there. When we talk about damped system, what do we have to do? We just have to avoid the modal frequencies. Forcing frequency, we should avoid the modal frequencies, as that is going to give us high amplitude oscillation. So we basically operate far away from the modal frequencies or the resonant frequencies. Okay, so this was for the multi-degree of freedom system. Now, if we have a choice to select whether we want to work with or model my system as a single degree of freedom system, as a two degree of freedom system, as a multi-degree of freedom system, it is our choice, right? But which is easier for us? Like for example, I have a system, okay, and let us say that this is only my system, and I'm giving a particular kind of an input that is near to a particular mode shape. So what is going to happen? It is going to excite only a particular mode shape and a particular frequency of oscillation. But I did the analysis for the whole n degrees of freedom system. So what did I do? I wasted my time. If I already knew that my system is going to operate in a particular kind of a vibration, right? What I can do is, instead of solving the whole equation, I can just find out that what is the frequency corresponding to that. And I can find the solution only corresponding to that particular mode shape. I don't have to find a general solution now, which is going to be a combination of n independent solution. Here, the general solution is going to be a combination of n independent solutions, right? But in any case, my system is just going to vibrate at what? A particular mode shape and a particular modal frequency. So what I can do is I can just model my system as a 1 degree of freedom system with that particular frequency. Okay, and I can just use that in order to model my system and get what the how the system is going to behave. Because if you remember that in the class, sir has also focused on this, and we also discussed about this, that if we have two frequencies, omega 1 and omega 2, right? Then at omega 1, x1 is going to have what? More contribution. X2 is not going to have that much contribution. Similarly, if we are going to excite the second mode, if we are going to excite the second mode, then only most of the energy is going to be inside that mode only. The first mode is not going to have that much energy. It is going to have some energy, but it will be very less as compared to the energy that is corresponding to omega 2, right? So likewise, if this is the case, that my practical system is always going to oscillate in a particular mode shape, and it is always going to have a particular modal frequency, then I need to only model my system as a single degree of freedom system with that particular modal frequency as the resonant frequency, right? And from that we can get what how the system is going to behave. Because maximum energy contribution, only this corresponding modal frequency is going to give. This mode shape is going to have the maximum contribution of energy. Others are going to have, but it will be very less as compared to this one. Okay. So this was for a multi-degree of freedom system. Now for the multiple degree of freedom system, if I want to find a solution, I've told you already, we are going to do what? We are going to find a general solution as a combination, or if we are exciting a particular mode and a particular modal frequency, we can just write the solution in terms of that frequency. Okay, I hope it is clear. Now this was all about single degree of freedom system, 2 degree of freedom system, and multi-degree of freedom system. Okay, these were the things that we talked about before going into the continuous system. I guess let me check for once if I'm missing something. Yeah, this was it. Then we talked about, for a multi-degree of freedom system, we talked about the point matrix and the field matrix. and the transfer matrix and all those kind of a things, which is some intricate terms, and we did a lot of questions also based on that. So I guess that must have been clear to you all. Now comes the continuous system, the concept of continuous system, and why is it even important? So see, we talked about the degrees of freedom, right? Over here in the first slide, we talked about degrees of freedom, right? But now is the point about continuous system. Now, what is a continuous system? Continuous system is nothing but the n degree of freedom system where n is what? Infinity. That is what a continuous system is all about. We had the option of choosing how many degrees of freedom that we want, but now we want an accurate solution. We want how the system is going to behave in a precise way, right? So what will we choose? We will choose to model it as a continuous system. The continuous system means we have infinite mass points. So if we have infinite mass point, it means we have infinite degrees of freedom and infinite frequencies. For a lumped system means lumped system is just an assumption of the continuous system which has only n mass point n degrees of freedom and n omega n. So for a lump system, we have a finite value of mass points and frequencies. It was easier for us to solve. But for a continuous system, we have infinite mass points, infinite degrees of freedom, and infinite frequencies. Now we cannot solve it using the concepts that we used earlier for the lumped mass parameters. For this, we need to define the equation in terms of partial differential equation. Why partial differential equation? Because in this case, my deformation or motion x is dependent on time as well as on x and time. Let us say it as u. Like for a cantilever beam, like this, u is dependent on what? Time and distance x. So this is a continuous system. Now, what were we doing in order to find out the equation of motion? We were differentiating the energies, or we were equating the forces and everything. We were doing force balance and all those kind of things. So we were getting an ordinary differential equation. Here we were getting the governing equation as an ordinary differential equation. But what about here? Here we were getting the governing equation as a partial differential equation. Why? Because our response u is dependent on two independent variables, x and time. X and time. Earlier it was dependent upon just time. Here it is dependent upon x as well as time. So the governing equation is going to be a PDE, which is a partial differential equation. Which is the partial differential equation. Okay. So we have a partial differential equation. Solving a partial differential equation is difficult, especially when we are solving it analytically as compared to the ordinary differential equation. Because for ordinary differential equation, we know how to solve. We have done it in our engineering mathematics courses as well. and there is only one variable, so integrating is easy. Here we have two variables, so integration is tough. But then we have done some problems which were related to bar, beam, and string, right? We did solve the equation and we got to the solution in the analytical form, right? But what is important over here is that we have infinite frequencies, right? And even if we use the model that we are using for the partial differential equation, we are going to get the fundamental frequency. Okay, we are going to get the fundamental frequency, which is going to be omega n. But what about the other frequencies? See, in case of string, if you remember in the last class, yeah, yesterday only we did that for the string, the fundamental frequency, if it is omega n, fundamental frequency is omega n, then other frequencies are what? They are the integral multiples of omega n, right? Do you remember? For the string omega n, if it was the fundamental frequency, other frequencies were the integral multiple of omega n. For the bar and beam, again we had different frequencies which we were getting from solving the equations, right? Which were transcendental equations, if you remember. Like we did it in the last yesterday lecture only, as far as I remember. So wait, let me see. Yeah, something like we did a numerical as well. Yeah, we did the numerical which was related to beta, tan beta. It was equal to J of rod by J. It was for the torsional movement, right? It was about the torsional movement. If you remember, there was this reference, there was this rod, and something like this. This was J naught, and this was J rod, right? So we were solving B tan beta. Beta tan beta is equals to J of rod by J naught, right? We had to find the values of beta. Beta was essentially which had the term for frequency as rho by G, right? So we had to solve for omega. We need to find out the omega. Now, if you remember this, how did we solve? We used the maths table. Now, this is a transcendental equation. This is a transcendental equation, which means that equation of the form that contains log e to the power sine cos tan or the hyperbolics of sine cos tan, something like that, not the algebraic form. So solving this is difficult. We don't know. We never learned about how to solve it analytically because it is difficult. Mostly it is solved by a trial and error method. Okay. So we assume that, okay, this could be the possible solution and we try to solve. If you use MATLAB, you can use many numerical techniques like, for example, Newton-Raphson method or the bisection method. No, in order to solve and get the values, but you can use the maths table. Now, maths table is going to help how? So, if you have J rod and J naught, and it is going to give you some value, let us say J. So, you can use the maths table to find out that for this to be equal to J, what are the possible solutions of beta? And once you get it, like for the case, for the yesterday case, we got beta as 1.135. Second one was 3.722, and likewise there were multiple. So what will we do? We will consider all these values and corresponding to these, we are going to get different values of omega n. And those are going to be the different frequencies. Likewise, it is going to have infinite values, but we are not concerned about infinite values. Why? Because in practical application, what were we doing? What were we doing for a single degree of freedom system? We were finding the resonance condition either to avoid it or to know that if a perturbation is given to the system, what is going to be the frequency of oscillation. Again, for the 2 degree of freedom or multi degree of freedom system, we were finding the natural frequencies and we were finding the mode shapes. For a 1 degree of freedom system, no matter what perturbation you give, which direction you give, it is always going to oscillate with the natural frequency, omega r, sorry, omega n, because there is only one natural frequency. Now, when you come to multi-degree of freedom system, the perturbation which is given, it will depend on how which mode it is exciting and what is going to be the modal frequency. Since there are multiple numbers of frequencies which are related to the mode shifts. So if you give a particular input which is near to a particular mode shift, it is going to excite that particular modal frequency. Likewise, in the continuous system, since we have infinite frequencies, we find some 10, 12 frequencies, so that when we excited with those frequencies, we know what are the mode shifts, and corresponding that mode shift, when we are going to get the frequencies. Now, when we are operating on a continuous system, there are two things that we need to learn about. First is, if the damping is small, then we avoid resonance condition. So we give the frequency in such a way such that the resonance condition is avoided. Second is, if we have damping present in the system, then in that case we try to avoid the resonance condition. Like if I am giving the damping, if I give perturbation, it is going to damp out. So definitely I'm going giving some external input, which could be in terms of excitation of the displacement or excitation of the force. This is going to excite the system. So we avoid the resonance over there because it is going to give us high amplitude oscillation. So we operate in a range which is away from those resonant conditions. Now for these continuous system, if we have infinite frequencies, we are going to have infinite mode shifts. Now for example, if I have three x, y, z direction, and I have constraint in the x and y direction, but in the z direction I don't have that much constraint about the movement. So I will look into the mode shapes and I will try to give it the frequencies that is not going to cause any trouble in the x and y direction, while for the z direction I will not be concerned because there is no constraint or limitation about the maximum amplitude of vibration. But then it is also important that it does not cause any kind of a catastrophic failure into the system. So that is how we analyze the continuous system, right? We solve these transcendental equations, find out the probable values of frequencies, and then get the mode shapes corresponding to it. I hope it is clear. Like we did for the string, if you remember, we got that for the string there is one fundamental frequency omega n, and the other frequencies are going to be what? They are going to be the integral multiples of this fundamental frequency, and corresponding to that it is going to have different modes. Like for the first mode, the string is going to be a string which is fixed from both end and is going to have a tension T. It is going to have a mode shape like this for the first mode, which is half of the sine, right? It is going to be a plot of sine from 0 to pi like this. For the second mode, we have frequency what? Twice. So if it is sine phi, this is what? This is sine of 2 phi. Anyways, phi is not dependent on time. Phi is dependent on what? L, length, from this 0 to L. So this is the first mode. Second mode is going to be what? Since this is sine phi, it is going to show us a full sinusoid, something like this, like this. So earlier we were having, this is going to be the second mode. So for the first mode, we were having a maximum value at what? L by 2. For the second mode, this L by 2 is having a zero displacement and it is also called as a node. Node means that it is going to have zero displacement. So for the first mode, L by 2 was having maximum displacement. For the second mode, L by 2 is a node, which means it is having a zero displacement, and the maximum displacement is at what? L by 4 and L by 4. Now, if you go into the third case, which is the third mode, Likewise, you are going to get the diagram. Okay, I hope it is understandable. You're going to have sine of 3 phi, right? So now the graph will go from 0 to 3 pi, right? 0 to 3 pi means what? Like this. This is going to be the shape. Now again, if you look, L by 2 is going to be what? Now it is again having a maximum. This is the third mode. It is having the maximum displacement, right? It is having the maximum displacement. Apart from that, now there are two nodes. There are two nodes now. In the earlier case, there was one node. There are two nodes, which is at the distance of L by 3 and 2 L by 3, right? So this was for the string fixed at both ends. Okay, so I hope that this thing is clear, that how are we going to model a continuous system. Anyways, these were some cases for the bar, the beam, and the string, which we considered because it was easier for us to get the solution for the partial differential equation of these. Anyways, it seems easier, it is not that easy. But when you talk about a practical system, we don't usually rely on getting the analytical solution because it's a complex system. So we prefer FEM analysis, finite element modeling. So we find out the FEM model, which is essentially a partial differential equation and depends upon the boundary condition of the system. Like this, the system was having a boundary condition, and if you remember in the last class also what we were doing, we were using the partial differential equation and the boundary condition to get the natural frequency. Similar is the case with FEM also. So we get the PDEs for the FEM. We have the PDEs, then we have the boundary condition, right? And then we solve it. The first way is anyways analytical, but it is not always possible to solve it analytically. So we use computational techniques. We can use softwares like ANSYS, SolidWorks, or COMSOL, and we basically define the geometry of our system. Okay, so for example, if you want to simulate a plate, something like this, a plate something like this, and if we fixed this side of the plate and let us say a force F is applied over here, and we want to see that how this force is going to affect the stress distribution and the strain distribution in this plate. So what will we do? We will make a 3D geometry of this plate. We will fix this end, let us say A. We'll fix this face, and then like particularly in ANSYS, we use static structural for this kind of a situation because we have a static loading on this plate. So we apply a force F in a static structural environment of ANSYS, and then we simulate it. But again, the accuracy of the results depends upon the mesh size. So mesh size means what do we do is, what the software does is, it creates a mesh. It divides the plate into multiple parts, right? It is going to divide the plate into multiple parts. It's going to divide the plate into multiple parts, and then it is going to do the or perform the numerical analysis. This is not solved analytically, it is solved numerically. So it performs a numerical analysis. Now, for the numerical analysis, if this is h, let us say a small cube is of size h, the smaller is the h, the better is the accuracy. But then the more is the computational cost. So there is always optimization between accuracy and the computational cost and time we are investing into solving the system. So we define the mesh in such a way that we get a good approximation of the solution. And it is generally preferable that all after solving these kind of a simulation, we usually try to validate the model and we create a same kind of a setup and then try to apply a force and see how practically it is moving. And then we validate our FEM analysis with this. And then we know that, okay, our FEM analysis and the number of mesh sizes that we have generated for the system, it is good to go for for a good solution. And then we can further analyze it. Okay, so we just created one sample or two sample, three samples, because in experiments there are some kind of a error. So it is generally preferable that we create multiple samples and take multiple data for the same condition and then take the average of those data to validate a particular model. So once we validate the model, now we know that our model is reliable, and now we can give certain other conditions and other kind of a forcing to the system and see the behavior. And then now after doing all the FEM analysis and everything, now we know that what kind of a behavior we want in our system, what kind of a material we want in our system, what kind of a dimension I want for my system, and then I can practically manufacture it and use it for a particular application. So it basically reduces the computational cost. The whole concept of doing a mathematical modeling is to reduce the cost of manufacturing and the safe make things safer, right? Regarding the safety issues, because if I apply a very high load on this bar, I know this plate is going to break, right? But how will I know that what is the limit of that force? I don't know. My intuitive understanding is never going to tell me that what is going to be the force. That is why experiments are very important and the FEM analysis are also very important. So we do certain experiments, validate our mathematical model, and now we can just do every kind of iteration I want to do with my mathematical model in order to understand how the system is going to behave in the practical situation. So this was all about this course. I hope that you people found the course interesting, and still if you have any doubt or anything which is related to the questions and everything, then you can mail me on my email ID, which I'm writing over here. Okay, then I'll be ending the session over here. All the best for your exams. Thank you so much.